Until now, we worked on the determinate system. We calculate the deformations of a statically determinate system. Now let's see how we can analyze an indeterminate, statically indeterminate beam structure. So let's take a continuous beam now. Let's say that this length is 8 meters. And this length is 6 meters. I have uniform distributed load. Magnitude is 24 kilonewton per meter. And let's call this point A, B, and C. Remember that this is a statically indeterminate structure, right? We have two equilibrium equations, and I have 1, 2, 3 unknown. So this is a statically indeterminate to the first degree. And we said that in order to analyze such structures, I have to combine the equilibrium equations with the compatibility equations. Okay, so let's see. Our starting point is we'll do the discretization. So here I have a node, a member AB, node B, member BC, and we have node C. Let's say that that's my first member, that's the second member, and this member is, oh, let's not show it loading here. Okay, so let's show the local coordinate system of the first member. That's x prime, that's y prime, and this is for the second one, that's x prime, that's y prime. And the degrees of freedoms are, I have a rotation, no degrees of freedom, no translation, rotational degrees of freedom, and rotational degrees of freedom. So in this structure, we say that we have 3 nodes, 2 members, and 3 degrees of freedom. Now let's draw the free body diagram. Of course, that's a statically indeterminate structure, so we won't be able to calculate the magnitudes of any moments, but let's draw it. Let's show all the forces. So we have a uniform distributed load here and uniform distributed load here. So let me show the moments. Let's say that I have a counterclockwise moment, MBA here, and let's say that I have a counterclockwise moment, MBC. I don't neither know the directions or the magnitude of these moments. Just I put 2 end moments. At these locations, I know that the moment is equal to 0 because I have a pin support here, and moment here is equal to 0. Now let's show the shear forces. I have VAB, VBA, VBC, and VCB. And let's put a note here. Moment is equal to 0, and moment is equal to 0. If I transfer these forces to the nodes, I have MBA here, MBC here. I got VBA, VBC. That's the reaction force B. VCB here, that's the reaction force C, and VAB, and the reaction force A. So this is the free body diagram. Now from that free body diagram, I know that the reaction force at A is equal to that shear force. Reaction force at B is equal to the summation of these two. and reaction force at C equal to VCB. The other thing that I know here is MBA plus MBC must be equal to 0. So I'm writing a nodal equilibrium equation for node B, and it tells me that the moment BA and the summation of moment BA and BC must be equal to 0. So this is what this free body diagram is telling me. The other thing that I know is the rotation at this end and the rotation at this end must be equal to 0, and it should be equal to theta B. That's the other thing that I know. Now all I need to do is to combine this information, theta B, these two rotations must be equal, and the summation of these moments at these 2 points must be equal to 0. I have to combine these two and see if this gives me a solution. So I need to relate these end moments with theta B. Okay, so in order to do that, I will be using the differential equations for bending deformation. But in order to do that, I need the equation for the moment. So let's take a look at it. Let's start from member 1. Okay. So I'm taking a section cut. That's the member. That's the x coordinate. So here I have moment M, and I got VAB here. So the equation for moment is equal to M is equal to VAB times x minus 12x squared. So I use this free body diagram to come up with this moment equation. Now at x is equal to 8, I know that the moment is equal to MBA. Now put that information into this equation. Now we have the following relationship. MBA is equal to 8 times VAB minus 12 times 64. Okay, and from that equation I obtain VAB as equal to MBA divided by 8 plus 96. Okay, so I obtain an equation for VAB. Now put it into that equation. I have my moment equation as follows. M is equal to MBA divided by 8 plus 96. I should have x here, sorry. 96x minus 12x squared. And this is the moment equation for the first member. Now let's do the same thing for the second one. Member 2. Let's draw the free body diagram again. That's x. So we have a moment. I got MBC here and VBC. Okay, and from that free body diagram I obtain my moment equation as M equal to VBC times x minus MBC minus 12x squared. So I know that at x is equal to 6, the moment is equal to 0, and put it into the moment equation. 0 is equal to 6 times VBC minus MBC minus 12 times 36. And from that equation I obtain VBC as equal to MBC divided by 6 plus 72. Again, do the same thing. Put that shear expression into the moment equation, and as the final step, this is what we get. Moment is equal to MBC divided by 6 times x plus 72x minus MBC minus 12x squared. So what I obtain here is moment equations for both members written in terms of MBA and MBC. Okay, why did I use MBA and MBC? Because I have a relationship between them. Okay, that's what I'm going to use to combine the equations. We will see. Now let's continue. Now we obtained the equations. Now let's calculate the deflections. So this is what I know about the deflections, right? Let's draw our classical figure. So at x is equal to 0, y is equal to 0, and at x is equal to 8, y is equal to 0, and dy over dx is equal to theta b. I'm writing the deflection again for member 1. So let's write the deflection equations for member 2 here. So let me draw the member one more time here. This is the second member. Boundary conditions at x is equal to 0, y is equal to 0, and dy over dx is equal to theta b. And at x is equal to 6, y is equal to 0. These are the things that we know. These are the boundary conditions. Let's start from the first member. Now, I'll just write the moment equation as follows, or differential equation as follows. EI d square y divided by dx square, and write down the moment equation. MBA over 8x plus 96x minus 12x squared. Integrated one more time, I got EI dy over dx as equal to MBA over 16 x squared plus 48 x squared minus 4x cubed plus C1. One more time, EI over y is equal to MBA over 48 x cubed plus 48 over 3 x cubed minus x to the power 4 plus C1x plus C2. Now I can use this boundary condition, and this boundary condition tells me that that's equal to 0, y at x is equal to 0, y is equal to 0. Now I have to calculate what C1 is, so I will use this boundary condition for it. So at x is equal to 8, y is equal to 0, this tells me that 0 is equal to MBA (8 to the power 3) divided by 48 minus 48 over 3, 8 to the power 3 minus 8 to the power 4 plus 8C1. And from that equation I obtain C1 as equal to minus 512 minus 1.333 MBA. Okay, and then I want to write or relate MBA with the rotation at B. So I will use that boundary condition. So I'll say that at x is equal to 8, dy over dx equal to theta b. Then I got the following: EI theta b is equal to MBA 8 squared divided by 16 plus 48 8 squared minus 8 cubed minus 512 minus 1.333 MBA. And when you simplify that equation, at the end of the day we get the rotation B as equal to 1 over EI 8 over 3 MBA plus 512, or I can write the following: the moment BA is equal to 3 EI over 8 theta B minus 192. So I obtained the relationship between the end moment and the end rotation for the first member. Now I have to do the same thing for the second member now. So let's do it. My differential equation is EI d squared y dx squared is equal to MBC divided by 6x plus 72x minus MBC minus 12x squared. So I'll do the same thing. Integrated EI dy over dx is equal to MBC x squared over 12 plus 36x squared minus MBC x minus 4x cubed plus C1, and EY y is equal to MBC x cubed over 36 plus 12x cubed minus MBC x squared over 2 minus x to the power 4 plus C1x plus C2. Again, if I put this boundary condition into that equation, I will obtain C2 as equal to 0 to satisfy the following boundary condition. And let's put this equation into this one to obtain what C1 is. So at x is equal to 6, we got y is equal to 0. And from that, I obtain 0 is equal to MBC 6 cubed divided by 36 plus 12 6 cubed minus MBC over 2 6 squared minus 6 to the power 4 plus 6 C1. And when you solve that, simplify that equation, we obtain C1 as equal to 2 MBC minus 216. Now again, I want to relate this boundary condition with the unknown moment. For that, I will use the following boundary condition. I say that at x is equal to 0, dy over dx is equal to theta b. And from that, I obtain EI theta b is equal to 2 MBC minus 216. Reverse the equation. and we have MBC is equal to EI over 2 theta B plus 108. So that obtain another equation that relates the end rotation, with the end moment. Okay, now I need to combine these two equations, right, to figure out what theta B is, and for that I will use the following equilibrium equation, right? At this node, the sum of the moments must be equal to 0. So I will be writing the moment equilibrium at node B tells me that sum of moments at B must be equal to 0. So MBA plus MBC is equal to 0. Now insert these equations into this one and into that one. We have the following: 3EI over 8 theta B minus 192 plus EI over 2 theta B plus 108 equal to 0. And when you solve that equation, we obtain the rotation at B as equal to 96 divided by EI. So that's the rotation at B. Once you determine the value of the rotation, you can put this one into these two equations and obtain these end moments. And when you do that, we obtain MBA as equal to minus 156 kilonewton meters and MBC as equal to 156 kilonewton meters. And since we know the values of these two end moments, if you go back to the free body diagram, if I know the value of this end moment, I can take moment with respect to that point and determine VAB. Then I can find out what VBA is. And I do the same thing for the second member. I can obtain these two values, and this will give me everything, all the support reactions. If I want to calculate the rotation values, I know now what MBA is. I can put it into that equation and make x is equal to 0. I can determine the rotations. Okay, so actually once we determine what this rotation is, we actually calculated everything in this structure. Now if we go back to our solution, as you see, it's a very long solution. I mean, in this structure we got only two members. Imagine what we have to do if we have more than two members and many unknown degrees of freedoms. Then the solution becomes much more complicated. So the question here is, how can I simplify this solution? I don't want to solve differential equations over and over again for every member, because it's very difficult. I mean, this is the simplest indeterminate structures that we have, because the degree of indeterminacy is 1. So what should we do? If you think about our solution, at the end of the day, we use the end deformations for every member, or the degrees of freedoms in the structure, and we use only the end moments. And by using the differential equations, so I solve everything for this member. I obtain the full rotation equation. I obtain the full transverse displacement equations. But at the end of the day, I use these two equations just to calculate the relationship between an end moment and the end rotation. I did the same thing for this one, calculated everything for the second member, but at the end of the day, I related the end moment with the end rotation. And since I have a relationship between the end forces and moments, I use the nodal equilibrium to combine these two moments, and this nodal equilibrium equation gave me the unknown rotation. So again, what I want to do is to simplify it, and this process, this solution process, shows me that I need a relationship between the end deformation of a member and the end moments of a member. If I can obtain a relationship like this, I can actually analyze indeterminate structures like that in a much simpler way. So my next aim is to again use this differential equations for bending, but in that case get a general equation that relates the end moments of a member with the end deformations. So our next step will be, we will take a member. Okay, this will represent a member for us, and it can have some loading on it, any loading, okay? And because of this loading, it can have a moment here. Let's call this point A, and it's point B, MAB, and this point will be MBA, okay? So this is the case where we have the end forces. Let's call it in a better way, member end forces. I'll just use the moments this time. And I want to relate it with the member end displacements. Again, I'm taking the same member. Okay, point A, point B. So here I can have a translation, right? Delta A, let's call it delta A this time. At point B, I can have a translation, delta B. So this is the chord of that member. But at the same time, I can have a rotation. Point A can rotate. So let's throw a counterclockwise rotation here, theta A. And point B can rotate. So let's have a counterclockwise rotation for B. Let's define it, theta B. And I can have a deformed shape in this member in the following form. Now the question I will going to ask is, what is the relationship between MAB and theta A, theta B, delta A, and delta B? And of course, the same question exists for the MBA. What is the relationship? And my next step is to figure out that. Let's repeat. Why do I need that? Why am I trying to relate MAB with the end rotations or end translations, or MBA with the same member end displacements? Because this solution procedure shows me that at the end of the day, in order to analyze an indeterminate structure, I will be using the end displacements and the end forces, right? And remember that when we do the discretization, we have isolated members and they talk through nodal displacements and nodal forces. And all I need to do to analyze an indeterminate structure, find out a relationship between them. This way I can combine the equilibrium equations and the compatibility equations to analyze an indeterminate structure. So this is what we are going to do next.